Your teacher today is Dr. Bosa, Science. Dr. Bosa is a teacher at the Science Foundation College, the best school that teaches sciences. Today we are going to study A-level Modern Physics, Lesson 2, the photocell. A photocell is a unit that changes radiation or light energy into electric current. The structure of a photocell is illustrated below. It consists of an anode made of a thin wire so that it does not obstruct the incident radiation, and a photoemissive cathode of large surface area to collect a large amount of light. The anode and the cathode are placed in the vacuum because the photoemissive substance is reactive. Applications of photocells. 1. Photocells are used to demonstrate photoelectric emission. 2. Photocells are used to determine the stopping voltage in order to derive the Planck's constant H, the work function, the threshold frequency, and the threshold wavelength of a particular metal. Photocells are used in automatic doors, alarm system, photovoltaic cells, in powering calculators and electronic watches, and production of sound from a film. Stopping potential. A stopping potential is the minimum potential between the cathode and the anode that prevents the most energetic electrons from reaching the anode. An experiment to measure the stopping potentials in order to verify Einstein's photoelectric equation and to determine the Planck's constant H. The setup is shown below. It consists of a photocell X, a filter F, a variable resistor P, a joke J, and an electric detector E. Procedure. A radiation of known frequency F is made incident on the photocathode. The emitted electrons travel to the anode and cause current to flow through the circuit. The current is detected at E. The PDV is adjusted until the reading of E is 0, or when there is no current flow. The minimum value of PD that prevents the most energetic electrons from reaching the anode, called the stopping potential Vs, is recorded from the voltmeter V. The procedure is repeated with light of different frequencies F. A graph of stopping potential Vs against frequency F is plotted as shown below. The following information can be obtained from the graph. A. Threshold frequency F naught is the intercept on the frequency or horizontal axis. B. The slope of the graph S is equal to h over E, where E is the electron volt. Hence, Planck's constant h is equal to S E. C. The nature of the curve verifies the photoelectric equation, i.e. Vs is equal to h over E F minus h over E F naught. D. The work function of a metal W naught is equal to negative CE, where C is the intercept on the vertical axis. E. The threshold wavelength lambda naught is equal to small c over F naught, where small c is the speed of light. F. When the experiment is carried out on different metals of different work function is, parallel graphs are obtained with a constant slope S equal to h over E as illustrated below. Note that the elements x, y, z have different work functions, but the graphs are parallel because they have the same gradient, capital S equal to h over E. Therefore, Planck's constant h can be obtained by using any element in a photocell. Example 1. Sodium has a work function of 2.3 eV. Calculate 1. Threshold frequency. From W naught is equal to HF naught. F naught is equal to 2.3 times 10 to the power negative 19 over 6.63 times 10 to the power negative 34 is equal to 5.55 times 10 to the power 14 has the stopping potential when it is illuminated by light of wavelength 5 times 10 to the power negative 7 meters. From HF is equal to HF naught plus EV, V is equal to H into F minus F naught over E is equal to 6.63 times 10 to the power negative 34 into bracket 3 times 10 to the power 8 over 5 times 10 to the power negative 7 minus 5.55 times 10 to the power 14 all over 1.6 times 10 to the power negative 19. This is equal to 0.186 V. explanation of the laws of photoelectric emission using the quantum theory. The quantum theory states that light is emitted or absorbed in discrete packets of energy called photons. 1. When light is incident on a metal surface, each photon interacts with a single electron, giving it all its energy. The photon is absorbed if its energy is greater than or equal to the work function. 2. Increasing the intensity of light increases the number of photons striking the metal surface per second. Therefore, the higher the intensity, the higher the number of photons in the incident radiation, and the higher the number of photoelectrons emitted. 3. Increasing the frequency of incident radiation increases the energy of each photon, and therefore the maximum kinetic energy of the liberated electron increases. 4. Increasing the intensity of light only increases the number of photons, but not the energy of each photon. Hence, the kinetic energy of the emitted electrons is independent of the intensity of the incident radiation. Failures of the wave or classical theory to account for the photoelectric emission. 1. Existence of threshold frequency. According to the classical theory, the energy of the incident radiation depends on its intensity. That is, the greater the intensity of illumination, the greater the supply of energy. This would imply that radiation of high enough intensity should cause emission even when the frequency is below the minimum value. However, as long as the incident radiation is below the threshold frequency, no photoelectrons are emitted. However intense the incident radiation might be. 2. Instantaneous emission of photoelectrons. Classical theory suggests that the energy of the incident radiation would be continuously absorbed by the electron, implying that electrons would take some time to accumulate sufficient energy that would enable them escape from a metal surface. By this theory, emission of photoelectrons would not be instant. 3. Variation of kinetic energy of the emitted photoelectrons. According to the classical theory, increasing the intensity of the incident radiation would mean more incident energy and greater maximum kinetic energy of the emitted photoelectrons. But instead, the maximum kinetic energy of photoelectrons emitted depends on the frequency of incident radiation rather than its intensity. 4. Variation of photoelectric current with intensity. When the intensity of illumination is increased, the number of photons incident on the metal surface also increases. Hence, more free electrons on the metal surface receive sufficient energy to escape. The rate of emission increases and therefore a large current flows. Thus, the size of the photocurrent depends on the intensity of incident radiation. However, according to classical theory, increase in intensity would increase the kinetic energy of emitted electron, and they would escape with greater speed, which is not true.